Hi, everyone. Thank you for being here today for this talk. So I will introduce to you Stephanie Shaya, who is CNRS Research Director at the POEMS team, which is a joint CNRS, Inria, and ENSTA team in France. Stephanie has a PhD in computer mechanics from École Polytechnique. And over the 2 past years, she has been as a visitor at Stanford University. Stephanie works on boundary element methods in wave propagation. And over like the 2 last years, she's been working on all these new applications at like trying to couple scientific machine learning and boundary element methods. So very interesting for what we do here at Inria Chile. And thank you, Stephanie, for being here.
Thank you, Paul, and thank you all for coming. So yes, I will go over the details of the title next, because first I would like to give you more details on what is POEMS. Since I'm here at Inria Chile, I think it's interesting for you to know her team. Since we are not doing machine learning, I'm pretty sure you don't know what we do. So as Paul just said, we are CNRS Inria ENSTA. We are located at ENSTA on the campus of École Polytechnique, so what is called Institut Polytechnique de Paris. And we are a big team for Inria and a small lab for CNRS. So we are something very unusual in France. So we are about 20 professors, researchers, and the same PhD candidates and a couple of postdocs right now. So what we have in common is that we all work on the modeling, analysis, and simulation of waves. It can be all kinds of waves, but we mainly work on linear waves. We have a wide range of competencies. So some of my colleagues are doing a theoretical numerical analysis, but we have also people more into HPC. So that's really what is giving us is to model waves. And some of us are from mechanical engineering and some of us are from applied math. So that's a very special team. If you want to do waves, you should come and see us. Okay. So the modeling for this work today is the design of marine seismic sources. So the idea is you use these sources to generate some waves that will be used to image the soil. And so I don't know why I cannot show. No, but okay. No, I wanted to show on the image, but that's okay. So what we're interested here is to model these sources. They know how to model the inside of the source, but we're interested in modeling the bubble of gas that is generated by these seismic sources. The first question is, how can we improve the accuracy of the seismic imaging? And for that, you need to make sure that you have a large frequency content, and in particular, you want to increase the low frequency modulation. So we want to be able to get an idea on what should be the source model in order to increase that. But what is really interesting is that to use these seismic sources, they also need to certify the high frequency content. And in particular, they need to show that they are not going to generate anything that will be harmful to the marine life. So they really need to rely on some computational simulation. Okay, and so now we can show the movie if you want. So it's to give you an idea. To model. This is the size of a bubble of gas that we want to try to model. Okay. Oops, sorry. So just to give you a brief idea of how we model bubble of gas and just to understand what we're going to do next. For sure, we have a very idealized model of what is the fluid behavior around the wave source. So we have an inviscid fluid, so we do not consider viscosity. We have an irrotational flow, so there is no vorticity. And because of that, we can consider a potential flow. So this is a very simple modeling of a fluid around the source. So in the next slide, you will see that I will introduce phi. And so phi is the potential from which is derived liquid velocity. And on top of that, we have an incompressible fluid. So at the end, if you use, I'm really sorry, at the end, when you add all of that, what you have to do, you have a problem that will evolve with time. And at each time step, you are going to solve a simple Laplace problem. Okay, really basic problem for the PDE world. But what is original in that work is that we solve this Laplace problem with directly boundary condition, but on a moving geometry. So that's what is making this problem more difficult. Of course, we need some kinematic condition to evolve the boundary of this bubble. That's really what we are looking for. And so you have the condition here. It's just derived from the gradient of phi. And in addition, we need to define some dynamic boundary condition to have, I'm telling you that we solve a Laplace equation with directly boundary condition, but we also need to evolve this directly boundary condition, and we simply use the Bernoulli equation for that. Okay, so because of that, that's a nonlinear problem. Okay. But when I've been asked to work on this, I was thinking, oh, that's a very simple problem for me because I know boundary element method. And since I'm pretty sure you don't know boundary element method, this is a brief overview of this very way less famous method than finite element method. The idea is that we are not going to use a variational formulation, similarly to what we will do with finite elements, but we reformulate the PDE into what we call the boundary integral equation. And the key point, and for everything we are going to do in boundary element methods, is that we need to use a Green's function to be able to rewrite the PDE as a boundary integral equation. So here you have the reformulation of the Laplace equation into a boundary integral equation, okay? So you see that in our example, we will impose phi, and we want to recover the normal derivative of phi. That's what we are going to do. And you see that it's called a boundary integral equation because it's not anymore a PDE. You have this integral, and this integral is only formulated on the boundary of your obstacle. And in that case, the boundary of the bubble, okay? That is evolving with time. So the main advantage of this method is that we reduce the dimension of a problem. We have a 3D problem, and now we just have to mesh a 2D object. So I just have to mesh the boundary of my bubble. And it's very well suited for infinite homogeneous domain because since we use the Green's function, we condensate all the information on the boundary of the domain. But then we have what we call a boundary integral representation to get the value in the full domain, okay, in the full 3D domain. So it's not that we are going to have the solution only on a 2D domain. It's just the method is decomposed into 2 steps, okay? And for sure, there is no free lunch, so it's limited to problems where we know the Green's function. So that's why this method is not so famous, is because you need to be in a case where you know the Green's function. And you know it, so and you need to know it, you need to be able to compute it in a fast way, okay? So in our case for the Laplace equation, in the ocean, where we consider that everything is homogeneous, that's the perfect method to be used, okay? And here you have some other example of application. So it's very useful to do some the evaluation of the scattering of some waves on an aircraft, for example, because we also have an infinite domain in that case. In the middle, you have an example of the propagation of seismic waves in a sedimentary basin. So if you consider that your domain is piecewise homogeneous, you can use this kind of method too. And the last example, if you can show the interaction between an underwater explosion and a submarine. So again, we can use the same method in the ocean, okay? So there are a lot of cases where it's useful to be able to do this computation. And we would not be able to do them with finite elements. That would be very too expensive. Okay, But in fact, to obtain this example that I have shown you in the previous slide, we had to develop what we call fast boundary element method. Because if you use boundary element method, you end up with a fully populated system, okay? So because we use the Green's function and because we have this boundary integral equation, in fact, we end up with a fully populated system, which is not the case with finite elements. The good news is that it's fully populated, but it's also full rank for sure, but there are a lot of information that are redundant. So that's what we are doing in fast boundary element methods. And that's where that's the starting point actually of this work on machine learning, okay? So we will be using what we have done for fast boundary element methods. So that's a key slide for my talk. Okay, so we have this fully populated system, and it's very expensive if you want to consider realistic configuration. So there is no way you will be able to simulate something that is realistic with this method. So we have to be able to find what is redundant and to remove it, to keep the solution accurate, but to reduce the computational cost. So here you have an illustration of how it works. We can simplify when the BM and say, I told you everything is related to this Green's function. So 1 over x minus y is the Laplace Green's function for the 3D full space. And what we are trying to do when we solve the BM, the most expensive part is to compute a matrix vector product between a system matrix and some given vector in an iterative solver. And at the bottom, you have a very simple illustration of the kind of operation that you try to do. You have a set of points x and a set of points y, and you try to compute u of x, that is the sum over y of 1 over x minus y times some function, given function f of y, okay? And the illustration with this cartoon is if you want to evaluate this for n points, and see the evaluated for endpoints, what you are doing is to do the interaction between a set of endpoints and another set of endpoints. And this is of order n square. So this is something, this is why we do not want to do it. The very rough way to simplify that is to say, okay, I don't want to compute all this interaction separately, but I will gather all the f to the center of mass of this set of points. And I'm going to transfer all this information once, and then I'm going to distribute this to all the points. So when you do that, you are doing a rank 1 approximation, but you end up with an order n algorithm. Okay, so that's the big idea. For sure, that's not what we are doing, but that's the idea behind the fast boundary element methods. What we do in practice is we do a data sparse representation of our matrix. So since the full matrix is not low rank, we are going to look for some blocks that are low rank. And to do that, we are going to decompose hierarchically our matrix, okay? And so we start from large blocks, which are full rank, and we subdivide them until they are low ranks. And we have some way to know in advance which block are low ranks, okay? So you have an illustration here where in green, you have the blocks that are low rank, and in red, the blocks that are full rank. And this decomposition of the matrix is done, actually, you start from your set of points, and you gather them in order to have points that are close by, because we will be able to do this low rank approximation for blocks that are well separated, okay? So everything is related to the distance on the physical mesh, okay? That's how we can gain to be able to model large-scale example with boundary element methods. Okay, so that's really a rough idea of what we are using. So far, I think I can say that the current state of the art is that we are able to use FastBM for a lot of wave propagation problems. It's very well suited when you have a given geometry. Okay, and if you want, for example, to do a parametric study with different incident waves, or if you want to consider a lot of sources, we have something that is very powerful. and we can also use it in the time domain. Okay, so we have, but we have way less works when we change the geometry, because every time I'm going to change my geometry, I will have to redo this low rank approximation, and that's really expensive. So we do not succeed to have something efficient for moving geometries. So if we go back to a problem of bubbles, why is it more difficult than I was expecting? It's because here I don't want to spend too much time on that, but here are some simple validation example for spherical bubbles for which we have a reference solution, which is given by the solution of an ODE. So this problem, in addition to be, this problem, I was not expecting that at all, but even for spherical geometry, it's unstable, okay? So I need to refine my mesh a lot to avoid to add some errors at each time step. So here at the bottom, you have an example. You see in blue, that's the reference solution. And on top of that, you have my numerical solution if I use a coarse mesh. So to have an accurate solution, I need to have a fine mesh. But even if I have fast BM, that's not fast enough to consider, for example, 10 to the power 5 time step. Okay, because even if if I need 1 minute to solve my problem, which is something that is already very fast in the BM community, we are very happy with, where we can consider a problem with, let's say, 100,000 degrees of freedom in 1 minute, we are pretty happy. But in that case, that's not enough, because it would take months to solve this problem. So that's the starting point of why I started to think about, can I use machine learning for that? Because I know exactly the kind of shapes that I will encounter, okay? And I'm okay to spend a lot of time to train something as soon, if when I use it, it's very fast, okay? I want to be able to use it in my time-stepping algorithm in a fast way. And so that's here where I have to say it's pretty new to me. So you are the expert, and so feel free to interrupt and give me some feedback for the following. And perhaps it will be very naive, but that's the way I understand what I have learned about machine learning and how I try to connect with what I know from BEM. Okay, so in this work, I'm trying to use machine learning in order to obtain the normal derivative of phi, knowing phi, and some geometry. Okay, that's my goal. And my understanding is if I have one configuration, what we are doing is we are trying to learn how to fit the data, but we are not really learning the matrix M. What I understood too is that if I use fully connected neural networks, usually you need to have the same fixed structure for all input fields, the same mesh, and that's really not what I want, because I want to be able to have different meshes, different sizes. I want no constraint on that, okay? I want to be able to refine my mesh if I want. And the key point to me is that in a fully connected neural network, the key point is to obtain the optimal structure for my neural network. And this is really related to the number of free parameters that you accept to have in your neural network. A key question to me, also coming from the PDE community, is I'm okay to get something, some solution for machine learning, but I need to know exactly what is the accuracy that I can obtain. So I will talk a lot about that. But first, an illustration on the solution of the Laplace equation on a sphere, but with various Dirichlet boundary conditions. And so here you have an example where I've been using 50 example to train this model with various Dirichlet boundary conditions. So you have here the loss function, and the accuracy I get for this model is okay, both for the training set and the test set. So I was pretty happy. But to get that, we had to use the neural network to mimic the BM matrix. So it's really not really interesting for you, I'm pretty sure, but it was really interesting for me to understand that if I put as many parameters as in my BM matrix, I get something that is accurate. which makes sense. Okay, we need at some point to have this information. And the reason why we did that is before we were trying with more usual fully connected neural network with less free parameters, and we were not able to get some accurate results. So at some point you need to correctly pick your free parameters and your structure. Okay, so the first thing I understood was that we need as many free parameters as in the BM matrix, because otherwise you do not have something that is accurate. But that's too expensive and makes no sense to use machine learning to do that. Okay, so now how can we reduce the number of free parameters? And the idea is we are going to use what we know from boundary element methods to define the optimal structure for this neural network. And there is already an article on this subject. You have the reference here, where they really use hierarchical matrices to define the optimal structure. Okay, so that's really the way they define it. Okay, so here you have what they are doing. So they use this hierarchical matrix structure to define the neural network. They use CNN to reduce the computational cost, and they have nice results for to solve the nonlinear to the equation. Okay. The good news is that's not exactly what we need for our work, because it would have been sad, but that's the end of the story. Because in this example, they are going to change the boundary condition, but they are not going to change the shape, and they are not going to change the discretization. So that's the additional challenging that we have in our example. So the question is, how can we define some neural network for multiple geometries? So we could increase the size of the structure of the neural network, but it will be too expensive, and at some point it will be inaccurate. Okay. Oops. So we are going to use graph neural networks. That's the best way to do it in order to leverage the flexibility and non-Euclidean structure of graphs. And we are going to use this graph to propagate and aggregate the information between the nodes that are connected. Okay, so here you have an example on the sphere on what we are going to do. We are going to define the neighbors to each node, and we are going to update the feature on all nodes based on the information of the neighbors. Okay, so here you have the definition of what we use from the neighbors and how we, but this is very classical, okay? So the key question again is, how do we define the neighbors, okay? Is it only the one neighbor that is connected, or do we increase that? And if we use all the domain, it will be too expensive. And the usual approach in machine learning is to ignore the longest range interaction. But if we do that in our context, it's similar to say that in my BM matrix, I set to 0 some coefficient. And that's not the case. We know that if we do that, that's not going to work. Okay? And we know also from graph neural network that if we use one layer, we will have only information for direct neighbors. If we add more layers, we have more information. But at some point, we are just oversmoothing. So it makes no sense to add all the layers, okay? So we need something to be able to add some long-range interaction for arbitrary shapes. And so that's why we propose this hierarchical graph neural network that is really based on what we know from fast multiple method. So the idea is that we are going to start from this fine graph, define from my mesh, and I'm going to transfer information from the short range on this fine mesh. But then I will be able to add some long-range interaction, but on meshes that are coarser, okay? So this is how it works. Yeah, so this is the short range interaction. And then I use I use an octree structure to define how I go from a fine mesh to a coarse mesh, and how I define the new nodes on my different graphs. I do the long range interaction at each level, and depending, you see that depending on the how fine or how coarse is the graph, I will have very long range or shorter range interaction, and then I will just propagate, go back to the fine graph. Okay, there is an additional challenge for this work. Is it, should we use graph neural network or should we use graph neural operators? Okay, so in the PDE community, everybody is using graph neural operators, from what I see, to learn the continuous mappings. And but originally, GNN was more to learn from discrete graphs. Okay, I like to present this because to us, the main difference between the two kind of where you put the vector v from the neighbors. Okay, so in graph neural operators, it's really similar to you are trying to find the operator. So you the v is outside the neural network. But on a graph neural network, usually this is an input parameter in the neural network. And this is a key point because if you compare graph neural network and graph neural operator, you see that graph neural network are less expensive than graph neural operator. It's because you are trying to feed data and not to find an operator, so that's not the same dimension. But you do not have geometric information in graph neural operator, whereas you have it in graph neural network. But you have operator info. Okay, so they have complementary advantages. So we are going to try to combine them. And the idea is we will start with a graph neural network. And at the once we have the output of the graph neural operator, we are going to apply again a graph neural operator. Okay, so we are going to combine both in order to have both the geometric info and the info on the operator. And by doing that, we see that at the end, we have 5 different types of graphs. We can have a usual graph neural network. We can have a graph neural operator. Then we have 2 versions that are hierarchical, where I apply the previous algorithm. And then what we call the geom GNN is the combination of both of them. And the idea is we should get long-range information. It should not be so expensive. We will get geometric information and operator information because this is what we want to record. And here you had some illustration of the shapes. I will show some over. So this is a comparison of the convergence of the 3 examples that are hierarchical because I cannot use it. I cannot use the algorithm that are not hierarchical. You see that in green you have a combined algorithm, and you see that's the one that has the best convergence compared to the 2 others that are really having similar behaviors. Okay. And here you have an illustration of the accuracy on some shapes. So I'm using 50,000 shapes and input data to do this example. And I had trouble for visualization to find the one that are way different from the others. It's just because I did not put too much time into that, but we are randomly generating shapes, okay? And so you have a target in the solution, and so you see that visually we have a good agreement, and I also compute the L2 errors for these different shapes. So this is something that is really acceptable in for our application. But to be honest, I need to compare the accuracy for all the example, okay? And that's, I want to be able to certify that I will always have something that is of the order of 10-2, 10-3, okay? So what you get on this plot is the error the percentile of examples that are below some error. For the most general approach, that is the GNN. Then you have the one that is using neural operators. And then you have a combined approach. And to be able to compare them, I've put this dashed line that corresponds to an error of 0.03, which is something that is accurate enough for the application we have in mind. So the red arrow show you when we cross the target error. And so you see that by using this combined example, we succeed to have 90% of our examples that are below the accuracy that we want to achieve for the training set and 60% for the validation set. But so it's way more accurate than the other example, and that's the first good news. But I'm still having an issue with this couple of examples that are really not accurate. And I'm sad because I was expecting to have the final results that were accurate all the time. But I made a mistake in running the test. But this is the understanding we have for why they are not working. So I took the worst example, and for all of them, I computed the error with respect to the value of my largest value of phi in my input set. Okay, so my phi is also randomly generated. Okay, I did not put any constraint on that. And you see that and also the maximum output when I do my when I compute my example. So this is the target that I need to achieve for this example. And you see that there is a strong correlation between the error and the largest value of phi in my input data. So if you have any way to explain why we are getting that, I will be very happy to have some feedback. And if it is usual or not, I would be happy to have that. Otherwise, I will refrain and add some constraint on my input data because everything is linear, so I can just scale and I do not care. Okay. And so I hope that now you are convinced that by using our knowledge on fast boundary element methods, we are able to propose some hierarchical graphs in order to improve how we incorporate the long-range interaction. And in addition, we are coupling GNN and GNO to have something that is accurate for multiple shapes. Thank you. And just in case, we have a postdoc position that is open at Poem, so feel free to take a look if you're interested. Thank you.
Thank you, Stephanie. Are there some questions here? Anyone?
Thank you. So you mentioned that when you move the geometry, you need to reconstruct the octree for the hierarchical matrix. There is any solution to do that in a more efficient way? And just to add to that, can you pull back the geometry to a fixed domain and do the computation first?
Even if I do that, I will change my Green's function. So the issue is the same. I will have to recompute the Laurent approximation anyway, I think so.
Other questions?
Hi. Maybe a basic question, but I didn't know you can numerically compute the Green's function. So I remember the Green function is associated to a perturbation of the original problem. Like it's obtained from another PDE problem.
The Green's function is the solution of your PDE when your source term is a Dirac delta function. So I'm sorry, I'm not sure I understood what. So in that case, we know exactly what are the Green's function, but there are some examples where you can use some numerical evaluation of the Green's function. That's your question? How we can get them in that case?
Yeah, like you know it analytically, or you can.
This example, I know them analytically, but there are some examples where we can compute them numerically. You can, in fact, write a system with boundary integral equation to be able to compute the Green's function. But then it's very expensive to do that.
Thanks.
Yeah.
That was my question.
Yeah.
Thanks.
There is a question from the chat from Jose Galas. Thank you for the presentation. I didn't catch if the instabilities were on the numerical BEM methods or on the PDE you are aiming to solve.
So physically, there shouldn't be no instabilities, and it's really because we are computing it. We have some approximation in the BEM when we do that, and what is happening is that since the solution of the BEM is used to update the shape of the bubble, so the geometry on which we are going to solve at the next time step. Yeah, I can go back. I will show you because I was not sure I would have enough time. So what we are seeing is that VAR are accumulating with time. So that's not physical. Yeah, that's what we see here on the bottom plot. What you have on in blue is since this is a spherical example, but I'm solving it with a 3D BM, I'm not imposing the sphere to remain spherical. But here the blue show you how I deviate from a sphere. So you see that at the beginning, I'm remaining a sphere, but at some point, the error that I have in my BM, which are the orange plots, are accumulating and are moving my geometry from being spherical. So that's really what is happening. We are accumulating the error. So we need to, at the same time, we are working on trying to understand why this algorithm is unstable and what we are doing in the solution that we should not do to make it stable. But that's really an issue from my side, from a numerical approximation.
Thank you for the presentation. I have a more question more about more basic about not so into the models and the equations. It's that I missed the relation between modeling a bubble of gas with the high frequency radiation that you mentioned that it was harmful for the marine life.
Oh, okay. So that's really not my expertise, but I will tell you what I understand. The bubble of gas, when it's moving, that's going to generate some noise too. And so they want to make sure what is the frequency contents of this noise.
Okay. And can I ask, like, if your institution or investigation center where you work,
my expertise is on fast BM. That's what I've been working on for the last couple of years. Okay. So you give me an equation and I try to solve it in a fast way. Okay. But I'm really not into the modeling.
Ah, perfect. Thank you.
Thank you for the presentation. I wanted to ask, I don't know much about it, but I have seen the operators network being used to solve boundary problems. But because you have a changing geometry, you add the other network. So, but couldn't you add a regulation parameter in the loss function to account for the geometry? Maybe? Instead of
you want to add some other term in the loss function to account for the geometry, but because I don't know how what can you think of what kind of because I understand when you add some term for the PD, where you add some term for boundary condition, but for the geometry, what is the, because I know the geometry, but
Like free parameters such that the same network kind of learns.
so what we did and was interesting was to add. First, we were trying just on spheres, and if you add the knowledge of a radius, you improve the accuracy of the neural network. I know that. But in that case, the graph has all the knowledge of geometry, so I don't know what I can add on top of that.
Now it's kind of abstract, so
Yeah.
it's hard to.
But perhaps, I don't know. To me, graphs are taking into account that part.
Thank you.
No more questions? Well, thank you, Stephanie,
Thank you.
for your talk. Thank you for everything.
Thank you.